Awesome. Thank you, Sam, for introducing the morning sessions. Hello, Devcon. I am Gubsheep, and I'm here to talk to you about hallucinated servers. Thank you for joining us on this morning. I know it's not easy to make the first morning talk of the day, so I appreciate everybody for making it out here. By way of introduction, I'm Gubsheep. I'm one of the co-founders of 0x Park. In particular, I work on a lot of applied cryptography projects from research to production. And today, I'm going to be talking to you about Frog Zone, which is a game that you might have seen downstairs if you swung by the Frog Crypto Community Hub. So downstairs at the Frog Community Hub, we have two tables of 4 machines each. You can log into one of these machines using your ZooPass by scanning a QR code, and you'll be dropped into this very simple frog game that I'm going to describe now. So this is a screenshot from the game. Essentially, Frog Zone is a 4-player game where you control one of 4 frogs on a 32 by 32 grid. So there's a 32 by 32 grid. There's a map. There's some items. There's some monsters. You can attack the monsters. You can pick up the items. You're trying to explore the map. You can only see the 5 by 5 area around you. And in a time limit of 5 minutes, you're trying to make it up north to the ice biome to find and slay the dragon. And this is a cooperative game, so even though you don't know where the other players are, all of you are going to have to collectively come together to figure out the right path to get up there and then use your combined items to finish off the dragon. So as you can see, my frog's moving around. I just destroyed some enemy here. Here I can see there's a wooden sword. I can go over to the wooden sword and pick it up. And if I do that, I should see my attack stat up there increase. So you can see, frogs have lives. They have different stats. Let's just watch that happen real quick. And as you can see, the rest of the game is shrouded in this fog of war, right? So I can only see the 5 by 5 area around me. And in short, it's a pretty simple game, right? There's a very, very limited set of mechanics. In terms of, the game in numbers, the total size of the game is about a total of 150 bytes. That's the entire state of the game. The front end is built in React and Phaser. The source code for the back end is about 500 or so lines of C++, not including boilerplate. That might be something like half of that. And it took about a month for a team of devs and collaborators from Gauss Labs and 0x Park and PSE to build this together. So why am I showing you this? Why am I showing you this incredibly simple game that a kid could have probably built as their first programming project? Well, essentially, the interesting thing about this game is that the back end of the game is running entirely inside of fully homomorphic encryption. And to our knowledge, this is the first time a multi-user application with a back end that is running inside of FHE has actually been built. So that means that all of the state of this game is encrypted using FHE, and all player actions and everything happening inside of the game is happening inside of FHE. Oh, thank you. So one question you might ask is, why bother running this inside of FHE, right? FHE is super expensive. Well, one thread that we've been pulling at in the last year is this idea that technologies like FHE can enable us to run what we think about as hallucinated servers. So let me describe what I mean by that. Today, if a group of us wanted to come together and to build some sort of application that all of us might use, like, let's say, a social network for Devcon attendees, the way we would do that today is that we would have someone rent out an AWS server, write some sort of back-end code, and then deploy that back-end code to the web server, and then each of us would, using our computer or using our browser or client or whatever else, talk to this back-end server, making API requests to update and retrieve the state of the application. Now, using technologies like programmable cryptography, another way we can imagine doing this sort of thing opens up. So we can imagine in a world with programmable cryptography that rather than there existing a specific physical server with a physical footprint that's running all of the computations of the application, instead, every participant of the application might store something like a cryptographic shard of the overall state. And using technologies like multi-party computation or fully homomorphic encryption, we could cryptographically simulate the execution of this virtual machine using things like ZK proofs or FHE to advance the state of this arbitrary computation one step at a time, ensuring its consistency, ensuring that everybody is only having access to the data that they're supposed to be able to, while doing so in a decentralized multi-party way without needing to rely on a physical server anywhere that actually is the source of truth for the system. So, this sort of opens up a lot of interesting questions. What if our digital services ran as these distributed hallucinated computations between just the relevant parties? We could imagine having this abstraction for a server where instead of servers run by Zuck, we have a server made of math that's perfectly secure, privacy preserving, verifiable, interoperable with every other service built in this way, etc. Of course, right now we're very early on our journey. So in terms of the game in numbers, in order to run this extraordinarily simple game, 150 bytes of state with 4 frogs on a 32 by 32 grid, we are using 9 machines to coordinate a variety of different MPCs together. So we have 4 MacBooks downstairs, and then we also have 5 192-core AWS machines in the cloud, costing us about $200 an hour to run this game. Every binary gate involved in the execution of any operation takes about 10 milliseconds to evaluate, which is about a 1 billion times overhead on top of ordinary computation. And for every bit of plain text state in this game, this bit will blow up to about 3,000 bits. Actually, I think this might be 3,000 bytes of ciphertext. I need to check on that, but it's a huge overhead. So the way that I think about what's going on is it's sort of like, we've built almost this particle accelerator and spent enormous amount of resources just so that we can suspend in the middle of the cryptographic ether for a brief instant something that looks like the Higgs boson, and we can sort of hold that stably. And in short, we have built what I believe is the slowest and worst performing game in the history of computing. Okay, so how does it work? Let's dig in a little bit to what's going on under the hood. So like I mentioned, there's about 9 machines that are concurrently performing various things together in order to hallucinate the state of frog zone. 5 of those machines are C6A 48X large AWS machines. They have 192 cores each, 384 gigabytes of memory. And then we've got our 4 MacBooks, which are our local clients that are involved in the decryption MPC. So whenever a player wants to make a move, move their frog up, down, left, or right, or attack a monster or pick up an item, they're going to send the encryption of that intent, of that request, to one of these 5 servers. That server is then going to share that encrypted request with all the other servers, and each of them is basically going to keep a replica of the fully encrypted state of the game. So that move is then going to be, shared between all of these massive servers and then executed inside of FHE to update the state. Now, in order to retrieve the latest state of the game, and in particular that 5x5 area around you, each of the client machines is going to be talking to a dedicated server that will handle the request of executing a view function on the overall state and then returning the result of that view function in encryption to the players. So we need 5 servers here because all of these operations are enormously expensive. We're using these machines to distribute the load of both executing in FHE all of the player actions, as well as executing the view functions over the state to return back to the players. Finally, because the state is returned back to the players in encryption, no single player has the decryption key for the whole game. In fact, no single party in this whole system has the blanket ability to decrypt and read state. So the 4 clients each contain a decryption key shard, and they have to coordinate using a simple multi-party computation in order to decrypt any individual piece of state. So I'm going to send out requests. That's kind of that big box, that switch in the middle of the 4 clients for those who have seen the machines downstairs. That is helping to coordinate the peer-to-peer networking that needs to happen for these machines to talk to each other. Okay, so what's going on with the servers here? I've described the idea that a hallucinated server would not need a physical machine that's actually the source of truth for the application state, and yet I just showed you a diagram where there's a fleet of 5 machines. Well, it turns out that in this case, the servers aren't theoretically necessary. What they're doing is they're performing a deterministic operation that involves no secret data. So they're basically just these, cattle which you can delegate computation to. They're performing these operations on top of encrypted data using a deterministic FHE scheme. Theoretically, we could run all these computations on the local machines and just have them cross-check each other, but for performance reasons, based off of where FHE is today, with the libraries we're using, Phantom Zone, we need to sort of add some additional computation power in addition to the 4 client machines that we have. So that's all that those servers are doing. I want to talk now about some tricks that we use to get a game working in such a constrained environment. So building out this game with the other collaborators has been a really interesting exercise. It kind of reminds me of what I've read about game development really, really early on, with the first personal computer games in the 90s, or even earlier than that, arcade machines. In a lot of these settings, game developers were working with very limited constraint sets. And for me also, this kind of reminds me of the early days of building blockchain-based games. So about 5 years ago, I worked on a game called Dark Forest, and this was before L2s. This was before there was widespread kind of toolchain support for ZK snarks. And you end up having to do a lot of interesting little hacks to even get something so simple working. So going back to our constraints, we have about the ability to work with maybe 200 bytes of plain text state. We have a 1 billion X computation overhead. We have an overhead that's somewhere in the thousands in terms of how big ciphertexts are, which have implications about how much state you can be transmitting over the network, especially here at a conference where tons of people are using bandwidth to find frogs or access their ticket, things like that. And one thing that we wanted to hold ourselves to was we wanted to keep each player action operating under 1 second. So every action that a player can take should execute in about 1 second, and that means that if all 4 players are constantly making actions, then players can be rate limited to performing an action once every about 4 seconds or so. So we want to be able to squeeze the most gameplay out of our constraints. And we can start by even looking at how do we represent player actions. So all of those different actions that you can see in the game, whether that's picking up an item or moving to a square or attempting to move onto a square you're not allowed to move to, or attacking a monster, all of those are simply serialized as 2 encrypted bits that represent a direction. And under the hood, what the FHE circuit is going to do is it's essentially going to execute all of these possibilities for what you're moving onto or what you're attacking, etc. It's going to execute all of that simultaneously. So what that means is the FHE circuit is going to take in the approximately 200 bytes of game state, as well as 2 encrypted bits that represent your direction, and it's going to check, for example, for each of the tiles that you should not be allowed to move onto, we'll do an equality check between each of those pairs of coordinates. And if any one of those equality checks turns up true, then I'm going to return your new coordinate as equal to your current coordinate and not equal to the coordinate that would be computed by incrementing your X or Y position. Similarly, with an item, we're going to simultaneously check for every item, is the coordinate you're trying to move to, that result of applying the direction on top of your original coordinate, is that coordinate equal to each coordinate of all of the items? And if any of the items turn up yes, then we're going to prevent you, or we're going to cause you to update your internal state to reflect the item upgrade that that item might give, and we're going to mark that item as consumed, and then we're going to refresh the entire state. So we basically have to figure out some strategy for factoring out the state into these different pieces and then running these checks efficiently over all of these different state coordinate pairs. Another thing that we have to be very aware of is the data constraints. So we don't want, when we're returning back something from the hallucinated server to a player for the decryption phase, we don't want to have to return a bunch of custom fields for all of the different kinds of entities that could live on a tile. In particular, because the computation that is returning what should be on each tile lives in encryption, whoever is making that return statement cannot know what's on each of those tiles. So we would have to, one naive way you could imagine implementing this, you could imagine implementing a big checklist that contains all of the items and all of the monsters and all of the, just all of the entities. And for every single one of the 25 tiles, it would it would return an encrypted bit for each checkbox in the checklist of whether that particular entity is at that particular tile. And because that bit is encrypted, the server, whoever's running the FHE, that could be a local client, would not know anything about what actually lives there. That's too expensive given the ciphertext blowup. So what we do is we have a 32-bit format, or it might be 40 actually, for what is actually being returned for any given entity. So we'll do some computation in the circuit. It will result in 32 bits. Depending on what those bits are after the decryption phase, that will tell you how to interpret these 32 bits. So the first byte tells you, various types of metadata, the entity type, the ID. Knowing the entity type tells you how to interpret the remaining 3 bytes. For the second byte, if it's a player or a monster, that represents the hit points. If it's an item, it represents the additional upgrade to your hit points. For example, the fourth byte, if it's a player, that represents score. If it's an item or a monster, that represents how many points you get for picking up the item or points for defeating the monster. And in this way, we can make sure that every tile that's being returned is simply this 32-bit thing without needing to special case for every single type of entity. Moving monsters was a fun one as well. So basically, you've got these 4 frogs that are moving around in the universe. Each of them can see a 5x5 square around them. But there's also a bunch of stuff going on in between each of the players' viewports. So monsters are actually these autonomous agents that are moving around inside of the global fog of war. There's some notion of global private state that is being executed on consistently, but which nobody in the game, neither players nor any of the delegated computation servers, know what's happening. So in order to do that, well, this is very expensive because for every monster we want to try to move, we again have to do that check of, is that monster moving to on a collision course with any of the boundary cells. So in order to make it feel like there's a bunch of monsters and they're moving in a reasonably performant way, what we have is we've just got these different kinds of monsters. One of the kinds of monsters is immobile, so we just never have to do this. Another kind of monster, we do have to do all of those collision checks. And then a final kind of monster, the bat here, it's a flying monster, so you don't have to do the collision checks, which speeds up things a lot on our end and still makes sense in the context of the game. There is a story about randomness here as well. So whether it's the initial conditions of the game or how the monsters are moving, you don't want any particular participant to know that, but you want that to be able to happen in a way that is correct and consistent with the execution of the program. So at every stage and at the beginning of the game, players are going to submit, they're going to randomly generate some randomness locally, encrypt that, and send that up to the server. The server is keeping an encryption of a global random state, and every time it receives a request, it can mix that in, and then it will use that randomness to seed various actions on NPCs or whatever else. So the direction that the NPCs move is determined by this random state. Okay. So that's the current state of things. You can try the game out downstairs. Just as a warning, it's very slow and very clunky and very brittle. I would not exactly call it a good gameplay experience. But you can play it, and you can try to slay the dragon. So another question to ask is, where do we go from here? Right now that we've demonstrated that it is in principle possible to build an application in this way, what might we want? Well, one thing that has become really clear is we might want more performance. Whether that means, adding a fleet of 10x more servers, or whether that means improving the underlying FHE protocols or the libraries that implement them. So with 10x more compute, we would be able to run this actually as a local computation between the 4 machines without requiring these delegated servers to help us perform these untrusted FHE operations. We could imagine procedurally generating the map itself. So imagine that rather than a fixed hard-coded map that is plugged in at the beginning of the game in Encryption, all of the players submit their randomness, and we use an algorithm like Perlin noise to generate a new map every single time that truly no one, not the developers, nor the delegated servers, nor the players would know. Another thing that's going on here is that in the process of building this, we realized that FHE as a technology is limited in certain ways. So I previously described how in order to make any operation on the game, you would have to feed the entire previous game state in, plus the mutation that you want to do on top of it, and run a state transition function over the entire thing in FHE. Well, that's not really how we think about programs today. We usually think about programs in terms of memory access. I can access such and such array element, I can update it, I can read, I can write to this. And that ends up being much faster because I don't need to carry the entire state with me on every operation. There's active theoretical work being done on FHE protocols and MPC protocols that might fit more naturally with the program, the memory model. One thing that's been really annoying, especially with the conference Wi-Fi, is the decryption stage that must occur between all 4 of the parties using technologies like obfuscation and functional encryption, which we discussed earlier this week. You would be able to make it so that the view functions, so long as you're calling the correct view function, can return to you the appropriate state that you want decrypted, so without a need for this kind of group decryption. So that makes the hallucinated server behave, at that point, almost identically to a server. We want verifiability, so whatever machines are executing the computation, the FHE computation, right now they can't learn anything about the computation, but they can execute whatever function they want. They could be executing some nonsense. And then finally, you might want something like a data availability layer. You know, if you want to add in properties like censorship resistance or certain forms of consensus, perhaps you want to treat FrogZone as something like a rollup. So that's an interesting direction as well. There's a few sort of conceptual or philosophical questions that arise as well, right? Like, is this an autonomous world? You know, somehow the bat that's flying around in encryption that nobody knows where it is, it has a kind of autonomy that is a different sort of autonomy from the kind that we get from blockchains and smart contracts, but it does feel like a new dimension. So what is the subjective experience of being a bat that lives in FrogZone, that lives inside of encryption? You know, maybe this is how we're going to do mind upload technology in the future. I certainly wouldn't want to upload my brain into the cloud in plain text, but I might do it if it's encrypted or obfuscated. So that's all for this talk. I just want to shout out a number of contributors who have made this possible. This was a joint effort. It was built on top of Phantom Zone, which is developed by Gauss Labs. A bunch of folks from PSE helped enormously in writing the circuits. Han, Edu, and CC. Sohan and Marian helped to build out the front end, and a bunch of 0x Parkers as well helped with the deployment of this. So that's all I've got for this talk. You can scan this QR code, by the way, for a froggy surprise. For those of you who have been playing the Frog Crypto ZooPass-based, ZK-based game, this will give you access to something special. But thank you all for coming to this talk, and we'll take questions now.
Woo! Thank you. Thank you, Gubsheep. We do have a few minutes for questions. I think it's going to come up on the screen. If not, I can read them. Can you elaborate more on the cryptographic primitives you used? Got into a bit. Curious if it's lattices to achieve the FHE.
Yeah, so one thing that's actually been really interesting about exploring this whole FHE world is that a lot of our old friends from ZK come up again. So, for example, one of the operations that folks might be familiar with that we have to optimize a lot during ZK programming is fast Fourier transforms and various kinds of polynomial operations. These things also come up in various FHE schemes, and we suspect that maybe they could be accelerated even with similar methods. FHE schemes also rely on some cryptography we don't see as much in ZK, such as lattices. We might have different strategies for approaching those, but this is very much an open kind of question. I don't think that what we're using right now for necessarily Phantom Zone or Frog Zone today is going to be what we use in perpetuity. But yeah, there's a lot of kind of these early exploration directions.
Awesome. Looks like some folks are curious, what is the most powerful use case you've imagined with this tech stack?
Yeah, so I mean, one exercise you can kind of run is like, what if you take the most ridiculous technology that exists today and just mash it all together? I like to think about this idea of a cryptomata, which is what I think of as cryptography's equivalent of AGI. So imagine that you had perfect obfuscation. It was running on a blockchain that had enormous data availability guarantees and bandwidth. What you would get is basically like a truly self-sovereign program that's made out of math, that's can never be taken down, it's always executing properly. You can never open up the program to inspect its internal state except as it is allowed to run. If you add in things like quantum one-shot signatures, that program might have things that can only be executed once. So it really feels like a physical program. And then you might think, what happens if you put an AGI, what if you run an AGI inside of that? Well, now you have this essentially autonomous being made of pure information that has first-class citizenship with reality in the same way that you or I do, or any living, thinking brain. So I don't know. The speculation here can get pretty crazy.
Love it. Looks like people are curious about code repos, about library usage.
Yeah, if you go to github.com/0xpark/frog-zone, you'll be able to see the code for this particular game. This is built on Phantom Zone, which is under the Gauss Labs organization. So if you're curious, come by the Frog Hub, and we'll get you set up.
Awesome. Another round of applause.